this is over the entire life of the program. So the program may have started off with one software development model and over the years changed to different ones. All those abstraction layers will still exist in some form. So this is kind of a useless process. But in the formal model, this actually exists. And in many cases, the assumption is basically made that we only care about user-level events, that we only care typically about what the user actually did, what commands they typed in, what buttons they pressed. We don't care about how many layers of abstraction there were between me clicking the save button on a program to it actually saving the file. That we'll kind of ignore those details for most cases. So this is a category, but it's not really done much in practice at all. So the next step here is we have three more, which are basically based on the same concept as the primitive levels, where we're going to say define the capabilities and then define the specific ones that occurred or existed. So the next one, number 6 here, is basically defining the abstract storage capabilities. So as we said before, these are based on what programs existed at each time. So to do this, we have to identify which programs existed each time and basically reconstruct the state of the system at each time. Determine which storage types exist in those programs, and then determine the possible states of those abstraction types. So, I mean, just the scale of this, just as a reference, consider that all the possible states of files is enormous. If you consider that there's 4 gigabytes or 2 terabyte maximum file size in your file system, all the possible states of those files is enormous. And the possible states of the system is basically all the possible file names and file combinations and files. So, I mean, the size of these sets is enormous. But again, this is kind of the beauty of theory versus actual practicality. And so basically, this is how we go about defining the actual possible states of the system. And to do this, we basically need to reverse engineer stored data. So if we have a Microsoft Word document or some other storage format, reverse engineer it to figure out how the data has been transformed and laid out and organized on the actual the file. There could be a specification for the file format we can use to define the different storage types. Or we could use some kind of dynamic and static analysis of the program to find out which ones are being used, or how the abstractions are being used. So in a similar context now, we have to define the abstract event capabilities. Again, identify which programs exist, what events they can cause. They basically map this in terms of what can actually occur in the system at each time based on what existed. And again, this is a process of using specifications if we have them, which we usually don't, and then some form of static or dynamic analysis of the programs to find out what the possible events were. And again, as I said before, in most cases we care only about user-level events. So this could just be as simple as running the program and playing around with it to find out what the possible user-level events are and what the effects of those events are on the system. And the final category of this is basically then, given these capabilities, given we know what states and events can occur and exist, to actually define which ones did exist and occur. And so basically this is making inferences about the abstract events and states. And there's many techniques of doing this. The 4 listed here are basically event and state abstraction, materialization, and then the usual reconstruction and construction. We have a diagram here, which is a little more complex than before. So basically reconstruction down in the bottom here, as we saw before, we have some known state. We want to reconstruct back to a previous state. The most common example of this in the abstract world is file recovery. So we have some deleted file in our file system. There's basically some event that we know of that deleted this file. We basically want to reconstruct the state of the system or the state of this file to before the deletion occurred. And so we use our knowledge about the deletion process and the file deletion event to actually reconstruct to what it was before if we still have the available data to do this. We also have now abstraction and materialization. So abstraction is basically, given the lower level data, apply the transformations that the programs would have to define these abstract storage locations. So the common example of this is we import our disk image in that has just basically a whole bunch of sectors in it, and we abstract this into a file system. So we abstract this from a disk into partitions, our partitions into file systems, and analyze our files in various levels. And so we start with low-level things and move up to higher-level data storage locations. And this can occur for abstract events as well, and going in all of these other various directions. And so there's some kind of dependence actually between these two, as we can notice here. That before we can define any of the other ones, we have to define the duration of the history, when this computer exists, what its times were. So this is kind of the main part in the whole dependency here. From there we can define what the storage capabilities were and the event capabilities were. And then from there we can actually start defining actual states and events. And similarly, after we have some states, we can then determine what programs existed, which allow us to determine which abstractions existed. So going to this picture here, this is probably too small for you guys to see on that screen. But down here is this notion of data abstraction, which is this analysis technique of taking those sectors from a disk, for example, and making a file system and identifying what files exist. For this process to occur, we actually have to determine what file systems existed and what files existed and what abstraction types existed, which requires us to know the primitive state of the system, which requires the primitive storage capabilities, and which requires an actual notion of the history duration of the system. So the benefit of this kind of dependency kind of graph is we can actually determine what assumptions are being made in practice when we go through this process, and a lot of these are actually skipped over in practice or can be skipped over in practice or just based on the assumption that they are true or that they are of various value. So if we examine the existing tools with these categories, we can basically break up our tools into two different categories. One is acquisition tools and the other is analysis tools. And the acquisition tools basically copy a state of a suspect's disk and make a copy so we can analyze it into a lab or some other location. And they basically, let me go back to the picture here, that we have original disks were being analyzed. At time t, we make a copy of this through a preservation program or preservation process. And at that point, we basically have two copies of the system from then on. And at time t prime here, if we want to actually analyze the system, we're going to use this to define a state of the system in the state's history. Now, ideally, we want to define this basically as being the state of the system at time t, which is when the copy was actually made. So we want to be able to say that even though this is 2 weeks later, we know the state of the system 2 weeks ago was this value. So to prove this, we actually have to show that nothing changed in this process. And this is what a lot of analysis tools will actually try and do. And the most common way of doing this is actually with MD5 sums or some other cryptographic hash value where you hash it over here at time t, and you compare the result at the current time to see whether it's changed or not, and we know whether we have an actual accurate value. And this is a reconstruction process that we discussed before in this primitive reconstruction, where we're basically starting with this state of our copy that we have and trying to reconstruct this state of the copy back to when the copy was actually made to verify that it hasn't changed over time. And the analysis tools basically, predominantly, allow us to define primitive states based on a copy where we can import some kind of sector-level copy of the system, define that in the system, and they basically make abstractions of files in various other forms. Chuck? Yeah, but the point is that the copy itself is then a file. Typically, it's a file from then on, and some other program in a system could have changed it, or it could have been maliciously modified to hide evidence. Essentially, from this time, what are we showing here? That from this time on, at that time t prime, it's completely independent of the actual system.